Okay, I think we're going to get started. So good morning, everyone. Thanks for coming through. And I'm excited to be here at Spark Summit in San Francisco. My name is Nick Pentreath, and today we'll be talking about pushing your Spark ML models to production using the portable format for analytics. So a little bit about me. I'm MLNick on Twitter and GitHub. I'm a principal engineer at IBM, where I work for CoreML, which is the Center for Open Source Data and AI Technologies. I focus on machine learning and AI, and I'm an Apache Spark committer and PMC member. So just quickly a little bit about CoreML. It is the relaunch of the Spark Technology Center, so that's the team I joined at IBM a couple of years ago. And the mission of the center has been expanded from Apache Spark and the surrounding ecosystem to encompass the end-to-end enterprise machine learning and AI lifecycle. So that includes the Apache Spark ecosystem, as well as Python data science stack and deep learning frameworks, and a couple of recent projects that we've released, the Model Asset Exchange and the Fabric for deep learning. So I encourage you to go check out codea.org, where there's more information about those projects. So today we'll cover a little bit about the machine learning workflow and the challenges of the deployment phase of that workflow. Then talk about the portable format for analytics in the context of model deployment and PFA for Spark ML, and wrap up with some performance comparisons and some future conclusion and future directions for this work. So as we all know, machine learning is simple, right? You start with data, you throw machine learning at it, and you profit. But in reality, the machine learning workflow is a lot more complex. So it spans teams, from your data engineers to your data scientists and researchers to your machine learning and production engineers. And they were all responsible for different phases of this workflow, and some of them overlap, from data through to ingest into your machine learning workflow and your typical data science workflow, which is all about data processing, data visualization, feature transformation, and engineering, through to model training, which is the typical model selection and evaluation, cross-validation type of workflow within a workflow. And most people think that that is where things end. Once you've found the best model, you're done. But actually, the deployment phase is critically important and often overlooked. So at deployment, you have to worry about deploying not just the model that you train, but the entire pipeline of transformations and feature pre-processing, and in fact, post-processing that comes with that. You have to worry about versioning and model management. And once you're in that live system, you have to predict given new data and do monitoring and evaluation. And that workflow also spans tools, in particular in that data science sub-workflow. So across languages, frameworks, and different runtimes, data scientists all have their favorite tools to use. And that entire workflow is actually a really small but very important piece of the whole puzzle. So the ML code that sits in the middle is maybe 5 or 10% of the entire application. And while it's important, it doesn't exist in isolation, and all of these other components that are part of that intelligent application are critical. And in particular, the serving infrastructure, and that we're going to talk about today, and how to integrate that machine learning workflow with that serving infrastructure. So machine learning model deployment comes with a set of unique challenges, and we've covered, we sort of hinted at them in the last couple of slides. So in that workflow, you need to bridge many different languages. Your data scientists are using R, Python, notebooks to do their exploratory analysis and conduct their cross-validation and model selection. Your production engineers might be using Scala, Java, C, Go, some more kind of high-performance language for their production systems. You need to bridge frameworks, so many you can't even list them. And there's a new framework, in particular in deep learning, being announced pretty much all the time. You need to manage various dependencies, versions. And the performance across all of these characteristics is highly variable. So, if you're just wrapping up a Python script in a Docker container, you don't really know if that is going to be performant in production. And this creates friction between teams. So your data scientists and your researchers, they always want the latest and greatest tools. So they might be wanting to train a model on the bleeding edge RC branch of TensorFlow to get the latest algorithm. But production doesn't like that, right? They want stability, control, and to be able to manage performance and have a good understanding of what the performance of that model is going to be when it is pushed to production. They don't like to be woken up at 2 a.m. in the morning with the system on fire. And from the business side, they don't really care whether you have deployed on Kubernetes or using the latest TensorFlow or PyTorch framework. All they care about is that the metrics are there, the product is always up and is working, and the business impact that they expect from that machine learning or deep learning product is there. So across all of these different frameworks and runtimes and languages, we have a proliferation of formats for models, data, and serialization. And this lack of standardization across all of these frameworks inevitably leads to custom solutions. And where there are existing standards, they have severe limitations, which effectively limit the benefit of that standard, because as soon as you have these limitations in the standard, you end up with custom workarounds and you lose all of the benefits. So we all love Spark, and we love Spark ML pipelines. They are elegant and performant and powerful, and they solve a lot of these problems, a lot of these challenges, because it's a unified framework for covering all of these different phases of the pipeline. And in particular, you can bridge this gap between having a trained model and deploying that in certain scenarios on Spark really nicely. But Spark comes with its own specific challenges. And because it is Spark, and because Spark ML has a tight coupling to the Spark runtime, it introduces complex dependencies and issues with managing versions. But more importantly, because it operates on data frames and uses the Spark SQL runtime, it introduces significant overhead when scoring, particularly in the real-time scenario. So that's due to query planning, task scheduling. Spark is effectively optimized for the batch scoring case or certain streaming cases, micro-batch settings. But it's simply not suitable for real-time scoring with very low latency requirements. And this is typical in recommender systems, online advertising, fraud detection models, anything where you need to make a decision in near real time is not going to really work with deployment on Spark. So currently, if you want to take that Spark model that you've trained and use it outside of Spark, everything is custom. You need to write a custom reader for Spark's native format, or you need to invent your own format, or you need to export to a standard format. But that's not currently supported, or has very limited support in Spark ML currently. And once you've even done that export to a format, you then need to load it up in some machine learning library, whether that's a custom one that you've written or some other ML library that's more suitable for real-time scoring. And so you need to write a custom translation layer. So one of the solutions for this is to use an open standard. And PFA, the Portable Format for Analytics, is an emerging open standard for deploying machine learning models and analytic applications. So it's being championed by the Data Mining Group, and the DMG previously created PMML, the Predictive Model Markup Language, which is arguably the only viable open standard currently in use, and it is in wide use. But PMML has many limitations, so it works very well for the stock standard machine learning models that it has built in, and if your problem fits well into the PMML spec, things are great. But as soon as it doesn't, it is very difficult to extend, except in a completely customized way. And once you customize PMML, you can't deploy it to any other scoring engine except your own, because that scoring engine doesn't have the custom components. So PFA was specifically created to address these shortcomings. So where PMML is XML-based format, PFA uses JSON for serialization and the format. It uses Avro schemas for data types. And what it tries to do is to encapsulate both the serialization format as well as specify the actual actions or functions that must be applied to the input of your pipeline or your model to create the output. So it really encodes the actual mathematical or linear algebra transformations that you need to apply. And because of the type and function system, PFA documents can be fully statically verified at runtime, and they can be scored in any compliant execution engine. So what this means is that you have true portability across languages, frameworks, runtimes, and versions. So I'll show you a simple example of what PFA looks like. So this is a multi-class logistic regression, and a PFA document is a JSON file or JSON document. It contains a bunch of fields, but the important ones here are input and output. So they are specified using Avro schemas. In this case, we have, apologies. In this case, we have an array, so a feature vector that is taken in by our model, and we return a double, a number. So that is going to be the predicted class. And the action is used to specify the set of functions that is applied to that input to create the output. So here we see a linear model built-in function, which is effectively a matrix multiplication or vector dot product plus the bias, so the typical kind of linear model predictor, followed by a softmax transformation, followed by an argmax, and you get the result out. So the functions that you apply here, and the JSON can be a bit tricky to read because it's really designed for computers to operate with, not really for humans. But the functions that you apply are really natural, and they're the same linear algebra and mathematical functions you would apply in NumPy if you're using Python, for example. So one of the things that are important in machine learning models and data transformations is state. So many transformers and models have some state, whether it's model coefficients or a mapping of categorical features to indices, etc. And PFA handles this by having something called cells. So we specify a cell, which is effectively a named value that is a sort of global variable. And we store, in this case, let's say a mapping. In this case, a mapping from a vocabulary of categorical features or strings to indexes in a vector. So this would be used for categorical feature encoding or vectorization of text, for example. So what's important here is that cell values are mutable within an action, but they are immutable between executions of that document. So you can update them during the transformation that you're conducting, but each time they're effectively reset. So they're a good fit for this model state. And you can also have globally persistent storage using pools. So they're analogous to cells, but they act more like a database entry, and they're mutable across action executions. Some of the other features of PFA is this concept of special forms. So you have effectively language constructs, control structures, conditionals and loops. You can create and manipulate local variables. You can have user-defined functions, including anonymous functions, cast, null checks, and some very basic error logging and exception handling. And importantly, a comprehensive built-in function library. So we saw an example of that earlier, but this covers linear algebra, strings, array, and map manipulation, mathematical functions, and some built-in convenience functions for common models, for example, clustering, linear models, trees. So there are a couple of reference implementations out there by the Open Data Group for PFA engines and for authoring PFA documents, DSLs, to make it easy to write them or convert from your machine learning framework to PFA. And those exist in Python and R, but not in the JVM world and not in Scala. So we at the Code8 team set out to create this. And this project is called Aardvark. So named because I'm from South Africa, and an Aardvark is an African anteater. And it literally means earth pig, so it runs around eating ants in Southern Africa. And there are two components. The core is a Scala DSL, so a generic DSL for creating PFA documents. And that uses Avro for S to automatically generate schemas from case classes. And then Aardvark Spark ML uses this DSL to export the Spark ML components to PFA. So here we see a recreation of the simple logistic regression example. And you can see that we have a cell, the linear model data, which is the coefficient and the bias or the constant of our linear model. And then that action is exactly what we saw before in DSL format. We apply the linear model computation, softmax, and an argmax. And then we just simply construct the PFA document. What's nice about Scala, and we can use the magic coming from Avro 4S, is that we can simply specify the inputs and outputs with type signatures here instead of manually creating Avro schemas, which is nice. Saves us work. So some of the challenges of doing this work include the fact that Spark ML has no schema knowledge that model has no schema knowledge. So once you've trained it, it knows internally how to transform an input to an output, but you can't inspect that model to extract what schema it expects, for example. So there's no sort of static typing. So this makes life a little bit more difficult, especially when you have multiple types of data that can come in. So typically, an example might be a binarizer. At training time, you know what the type of that column that you're binarizing is. So that transformer can operate on numerical columns or vectors. But at training time, it's not going to operate on both. So ideally, a Spark ML model that is trained, the model form of that, would actually fix that and not be able to transform the other type. So it wouldn't be an error if you threw a numerical column into a model that is actually expecting a vector column. So this just makes life a little bit more cumbersome. You have to do union types in Avro and so on. But it's not the end of the world. Combining components into pipelines and automatically exporting pipelines is certainly doable, but a little bit more tricky. And the current approach mimics passing a row object. So a row is a bunch of fields, and an Avro record, and you can think of it as also a sort of piece of JSON, looks very similar to a row conceptually. So really we aim to pass a record or an Avro record from transformer to transformer, and we merge each of those components. So first we convert that individual component from Spark into PFA, and then we merge them together, and we wrap each component as a user-defined function in the merged document. So it ends up being fairly verbose, but fortunately, you're not really expected to read through the JSON, and it's just for machines. So it does work, but certainly it makes life a little bit more complex. One important thing is that at the moment, PFA doesn't support mixed generic vectors. So you either have to specify a dense or a sparse vector. And this is a problem because in Spark, which makes sense, you can pass in any vector. So it could be dense or sparse, and it's generic. And Spark can operate on that. The Spark ML model can operate on that without any worries. So that's actually something missing in the PFA spec, and something that I believe needs to be changed and added. So that would make life significantly easier. So we've talked about PFA, and in particular the Aardvark project for exporting Spark ML to PFA. But what else is out there? So I mentioned PMML earlier, and that is a model format in XML. It's very widely used and supported. It's an open standard. And if it fits your use case, it works very well. Performance is good. There's no native Spark support for exporting to PMML, but there is a third-party project, which is JPMML Spark ML, worth checking out. It has very comprehensive support, which is perhaps a bit surprising given the potential shortcomings of PMML, but it does work really well. There is a current open JIRA in Spark to add PMML support natively. And there's a lot of other exporters for various popular frameworks. But as I mentioned, some of the shortcomings is that it cannot represent any arbitrary model or analytic application or program. And if you want to try and represent those, you end up customizing things to the extent that you lose the benefit of the standard. So it effectively doesn't work at any, once you hit one of those edge cases, you can't use it. MLeap is a very interesting project created by CombustML, a startup out of San Francisco. They've presented at many Spark summits. So it's created a standard or format in JSON and protocol buffers for exporting Spark ML models, and then you import them into the MLeap runtime. And those components are implemented in Scala code using linear algebra libraries in the JVM. So performance is very good, and they were initially focused on Spark ML, so the The coverage of Spark ML components is virtually complete, so very good coverage, very good performance. They're working on adding scikit-learn and TensorFlow. So it works really well, but I think some of the shortcomings is that the project has created a format which is open, in that it's open source, but it's not standard. So it doesn't have a concept of well-defined operators or functions that you can kind of mix or match or create your own user-defined functions from. And it forces this tight coupling between the consumer and the producer and the consumer. So if you produce a model from a certain Spark version, your MLeap runtime has to match that version. So that means either you need to run multiple versions of MLeap in production, or you have to have MLeap be able to read whatever Spark version the model is coming from and adapt accordingly. So that really creates that tight coupling, which is pretty tricky. And then this may not be a problem for some folks, but you have to implement everything in Scala. So now if you are a data scientist or an ML researcher, you might prefer Python or R. So the advantage of PFA is that using either the Scala DSL, the Python, or the R DSL, you can author documents or you can create an export library in your own language that you enjoy, rather than having to write everything in Scala. And finally, the Open Neural Network Exchange, or ONNX, is a protocol buffer format championed by Microsoft and Facebook. It's focused on deep learning, but it is very similar to PFA in the sense that it describes this kind of computation graph, including all the operators. So it describes the input to that graph and all the operators that are applied to that input to create an output. So it's a self-describing document, very similar to the PFA JSON. It is more focused on deep learning and tensor operations. So as such, the main shortcoming with ONNX at the moment is that there's not much support for traditional machine learning, and in particular pre-processing, tree-based models, control flow, intermediate variables, user-defined functions, and so on. So performance is always important. And what we did here is we compared the performance of PFA with Spark and MLeap. And for PFA, we used the Hadrian reference implementation on the JVM. The pipeline consists of string indexing 47 categorical columns, and then assembling those together with 27 raw numerical columns and doing a simple linear regression. So it's a pretty simple pipeline, and we tested on 80,000 records. So the average execution time for MLeap is about 0.3 milliseconds for this, and for PFA is about just over 1 millisecond. So PFA is slower than MLeap at the moment, by about just under 3 times, which is something that we definitely want to improve. And I think it can be done with improvements to the scoring engines and the reference implementations. But Spark cannot even be on this graph, right? Because Spark runs at 1.9 seconds per record, whereas these other two are single-digit millisecond or below. Okay, so in conclusion, PFA provides an open standard for serialization and deployment of analytic workflows, true portability across languages, runtimes, frameworks, versions, and it splits that model producer from the model consumer. So you have this true independence between your machine learning framework that's producing the model and your scoring engine that is scoring the model. All you need is to produce valid PFA from your model producer, and you need a valid reference implementation that can then read that document. So we believe this solves a huge pain point for the deployment of Spark ML pipelines in a standardized way, but also benefits the wider ecosystem. So as we saw, many of the kind of popular frameworks out there, gradient boosting libraries, scikit-learn R, already have PMML support and have exporters for that. And any PMML document can, in theory, be expressed as PFA. So all of these frameworks can also be exposed via PFA, and then one can use the same scoring engine for all of your model producers across whatever framework or language they are. So there are risks. I mean, PFA is a young standard. It still needs to gain adoption. We hope that we can help with that. We hope that you can help with that. As we've seen, performance in production at scale is relatively untested, and the tests that we've done so far certainly indicate that the reference engines need some improvement on robustness and performance. But what's encouraging there is there's no reason that you can't write a PFA scoring engine in C++ or Go or Rust. So that immediately gives you huge performance boost potential, and all your existing PFA documents that you've exported can immediately be run in that engine. The deep learning is obviously very popular right now. There's no built-in support for tensors or GPUs or tensor operations in PFA at the moment. There's no reason that it can't be added to the standard, but these things take time. A standard has many benefits, but certainly one of the downsides is that it can move really slowly. So fixes and enhancements to those standards are effectively done by committee, not unlike open source projects within foundations, so things can take time. So I'm excited today to announce that the Code team is open sourcing Aardvark, and it's available on GitHub right now. The current coverage has almost all Spark ML models or predictors, many of the feature transformers, basic pipeline support still needs work, full equivalence tests between Spark and PFA for all supported components, and tests for the core DSL as it stands now, which is certainly not yet fully complete. So we'd like to encourage you to go check out the project, and we need your help to finish implementing components that are not yet supported, to improve pipeline support, to complete the Scala DSL, add Python support for PySpark, test it out, to tell us where it's not working, help us with tests and documentation. Some of the things we want to work on in the future is adding, moving beyond Spark ML pipelines and looking at other libraries, starting with scikit-learn, XGBoost, LightGPM. Further performance testing, look at more automation and magic to translate from Scala to PFA. And importantly, propose some improvements to the PFA standard, in particular, as we mentioned, generic vector and tensor support, better schema definitions, and improvements to the reference engines, as well as explore if there are ways that we can add deep learning support to PFA. So that requires deep learning specific operators, perhaps some concept of operator graphs and GPU support. So thank you. I appreciate your time. I encourage you to go check out the code.org site and have a look at the newly released Aardvark project. And there's a bunch of other IBM talks that I encourage you to go to, including one later that I'll be giving about model parallelism in Spark ML. Thank you very much. Do we have time for a couple of questions, I think? Do you have a mic? Or?
Cool. Hey, when you said it wasn't tested in production at scale, what did you mean by scale? Like, what scale has it been tested at so far?
At the moment, scale would be really not so much the number of records, because it's real time, so it's designed for kind of record at a time, but really the complexity of the pipelines or the dimensionality of your data. So as the number of categorical features, for example, increases, and your model sizes get bigger and bigger, the execution time is going to scale in some way. And we've done tests for a few hundreds of features, but really, you need to have efficiency for thousands or tens of thousands or hundreds of thousands or more. And Spark is in particular at that scale for sparse feature support. So that's still outstanding.
Hey, a couple of questions. First one is that when you train the models, do you have to integrate it with the library to save it as with that format? Is that how it works? For example, in MLeap, typically you just save it as the usual Spark format, and then you can read it. And while reading it back, it uses the library, but not while saving, right?
So at the moment, the library just provides some helper functions. So you'd call to PFA. We're looking at adding implicit converters, but effectively you take the model, call to PFA on it, and you get back a JSON representation, so a string, and that you can do what you want with. You can immediately load it in a reference implementation. More typically, you will save that to a file system or to an object storage, or deploy it via REST API to your model server, something like that.
Right. Okay. That's one. And the second one is that is there do you share the code for the test that you perform? You mentioned that test between MLeap and
sure. The code that we were working off is using some proprietary internal data. So we're going to redo tests with some open data sources and just post those. So that's still a work in progress. We'll do that soon.
So that test code is not available currently?
Sorry, say again?
The code for that comparison test between MLeap and...
So that code is not open at this point. Simply because nothing about the code we can release easily. It's just that the data set, the particular data set was an internal data set we were working on with a certain product team. So we can't release it in that form because we can't release that data. Right. So we'll redo it with, with
like
some open data sets
set
that we can release.
And yeah, that. Thanks.
Unfortunately, we're out of time, so
thank you, Nick. If you want to, you can come up at the back, and if you want to ask some questions offline.
Yep, that'll be great. Thanks, Nick.